So thank you again for bringing a packed house. It's always great. So this seminar is a mix of advances, so theory and also applications. So today is our first day on applications. It's on the recommendation systems, and we have 3 industry speakers here today. We have Layer6, Wattpad, and Rubikloud. Unfortunately, our speaker from Shopify fell sick this morning, so it's just going to be 3 speakers, but we'll have a little bit more time for Q&A. All right, so the first speaker, we're going to start with Layer6. We're going to start with Guang. Guang joined us as a professional master's student in 2013, and he's going to be talking about some of our exciting work.
All right, thank you, Tommy, for the introduction. My name is Guang, and I'm a data scientist at Layer6 AI. It's truly a pleasure to be standing here and sharing some of our work at Layer6 with all of you. So first, why are we studying recommender systems? Well, there's over 3.7 billion users online today, and that's over half of the world's population. Massive volumes of data needs to be surfaced to these users, and recommender systems are the tools to do so. Netflix has reported that the economic value of their recommender system is worth over $1 billion per year, and that's back in 2015. And Amazon has reported 35% of the sales are coming from recommendations. In recommender systems that are currently deployed rely on collaborative filtering, or CF, and CF approaches leverages preference patterns from many users to build individual models for individual behavior. Of the CF approaches, latent models are the most commonly used. In latent models, users and items are modeled by latent factors, and that summarizes the preference information. The main advantages of the latent models are robust performance, compact indices, and efficient inference. However, traditional CF models fail when there are no interaction data, and this is a problem known as cold start. Cold start occurs in virtually every single domain when there are new user or anonymous user and new items joining without prior information on the interactions. And failure to address this problem leads to user churn and directly impact the growth. Content information is typically employed in order to address the cold start problem. A number of hybrid approaches have been proposed, which combines the interaction information with the content information into a single model. However, these models often employ a complex multi-term objective functions which are hard to tune, especially for large data sets. As an example, shown here is collaborative deep learning, or CDL, which is a popular hybrid model combining collaborative filtering terms with additional terms to account for the content information. Shown here, we have 6 hyperparameters that needs to be tuned in order to incorporate these preference and content information, making this model very difficult to tune when we have large data sets. So at Layer6 AI, to come up with a scalable cold start recommender system, we first aim for a simple objective that can be trained efficiently on large data sets. Next, we realized that content information is critical for these cold start problem, and deep learning is an excellent tool to capture a multitude of the content types. Yet, there is a lack of research on scalable deep learning models, and our work aims to fill this gap. The works by Max Volkovs, Tommy Poutanen, and myself at Layer6 AI that addresses this problem is the Dropout net. Our goal was to develop a latent CF model that generalizes to cold start and can leverage deep learning for the structured content and is easy to optimize in production. Our approach was to focus on the input instead of the objectives. And that is, cold start can be thought of as a missing input problem where the missing input is a preference information. We can then explicitly condition for this by stochastically applying a dropout onto the preference input. In our dropout net framework, we start with an existing latent model whose latent factors capture a relevance score S. Then we apply two sets of neural networks which map the latent vectors into a new content-aware latent space by passing the preference and the content information through successive layers of artificial neural networks. And the output, which is the content-aware vector, are shown by U hat and V hat. During training, this model is optimized to generate latent vectors which then reproduce this relevance score. And shown here is the loss function that guide this training. As you can see, compared to this hybrid model such as CDL, this model contains much fewer terms and is much easier to optimize because it has no hyperparameters. And to condition this model for cold start, we then apply a dropout on the preference input of user and items, which essentially forces the network to learn how to only use the content information to then generate the latent factors. Some of the advantages of our models are, one, our models have a very simple objective with only one hyperparameter. And in fact, we have found that empirically, when we're training this approach, as you might have seen, we actually don't have a regularizer terms on the objective. And this is because the dropout approach, in addition to conditioning the neural network for cold start, it's also preventing overfitting. And we found that it's unnecessary to have further regularization terms. Second, our model can be trained on top of any existing latent factors by simply swapping out the preference input with the latent factors from your existing latent model. And this minimizes the implementation barrier of our approach. Finally, both the user and item networks can fully utilize the latest deep learning architectures for structured content such as text, audio, image, and video. The entire model can be trained end-to-end. So for example, if you have a music classifier with acoustic models, you can remove the classification layer and put the rest of the model as input to the dropout net. Then you can either transfer the weights or train the entire model end-to-end from scratch. One interesting characteristics that we've observed with the dropout net is when we vary the dropout rate. Sorry. So So shown here, on the x-axis, we vary dropout rate from 0 to 1, which is a probability with which the preference input is set to 0. On the y-axis, we have recall at 100, with higher recall being better. Here we have two evaluation sets, which is one is warm start, where for every user and item, we have previously observed preference information during training. And for the cold start, we do not have previously observed interaction information. And at every dropout rate, we train one single model and evaluate on both of these validation sets. You can see that even with a small amount of dropout rate, the network is learning to utilize both the content information as well as the preference information. And we see an immediate generalization into the cold start problem. As we continue to increase the dropout rate, the model continues to do better on the cold start. But interestingly, on the warm start evaluation, the performance drop is negligible, up to a very aggressive dropout rate of 0.8. This means even when in our architecture, even when it's only seeing 20% of the preference information, the network is still able to learn how to utilize those information in order to generate adequate warm start recommendations. And now I'll show some of the results from two of the data sets. The first is the publicly available job recommendation dataset from Xing, an European analog of LinkedIn. This dataset consists of over 1 million users and jobs and 300 million interactions. We have both the user profile information and item content information, which makes it an ideal dataset to study cold start recommendations on. We compared our dropout net to some of the state-of-the-art hybrid latent models and show the results here. On the x-axis, we examined the performance at various truncations with which we evaluate the recall. On the y-axis is the recall, where higher recall is better. Our model is shown in light blue here, and as you can see, our model outperforms the state-of-the-art model substantially on the cold start user and cold start item datasets, evaluation sets. However, on the warm start, we're still able to perform favorably against these state-of-the-art models. One interesting observation we made is when we transition from the cold start to a slightly warm start regime. Here, we take the warm start evaluation set and remove all the interactions at test time, and then incrementally show the model more interactions per user. On the x-axis, we show the number of interactions presented during test time to the model, starting from 0 and going to 5. On the y-axis, again, we have recall at 100, with higher recall being better. Compared to a standard warm start model, our model without retraining is able to perform substantially better as these interaction informations are becoming available. And note that with warm start model with a traditional CF model, you need to retrain this model every time to incorporate these new interaction information, whereas in our model, it's able to do so without retraining. This is a profound result, especially in industrial applications where in many systems where you have new user or anonymous user, which starts as cold, and over a short period of time, they will accrue increasingly more interactions. And our model is able to take that into account and generate better recommendations in real time. Next, we compared our model, which was in this Rexis challenge. This challenge included both an offline and an online phase. During the online phase, the top models were subjected to a live A/B testing for 5 weeks, where every day of the week, new jobs are presented to the system without prior interaction, essentially posing the cold start problem. Traditionally, the winners of these models, the winner of these competitions would win by a small margin. However, this year, our team from Layer6 AI, with our approach, was able to place first decisively with over 12%, with about a 12% improvement over the next best model on the online phase. Finally, we show the performance of our model on one of our large-scale proprietary dataset to showcase the scalability. This proprietary interaction data contains 100 million users and 2 million items, and over 3 billion interactions. We generated 100 recommendations for each user, and that's over 10 billion recommendations in total in just 12 hours from end to end, and while substantially improving over the existing proprietary CF approach. So to summarize, we have presented Dropout Net, a novel deep learning approach for cold start in recommendations. Our proposed architecture is flexible, and can take advantage of the recent advances in deep learning for the content types. During training, there is only one hyperparameters that needs to be tuned, which we have shown to be very robust in our architecture. And therefore, we can apply this model to a very large data set with over 1 billion interactions, as we have shown. Finally, we demonstrated state-of-the-art performance on 2 large-scale data sets, one public and another proprietary. Our code is available publicly on GitHub under our Layer6 AI Labs page, and you can read more about both the data sets and the results in our paper in NIPS. Thank you. Okay.
So say a little more about the online training. Does that mean that you've trained it up, and now you're going to fine tune it with some new data on the individual, or do you match the individual? How do you do the online?
So for this online competition, the users and the users stay the same. So it's the users that we have seen, but the items are cold start. And we found that we were able to perform very well with the same model that we trained just on the offline data. So we're essentially rely on the new interaction and content information as input, but the model weights remain the same. Yeah. Yes.
You had a recall curve where the warm start was doing worse than the cold start?
Oh, so the data sets are different. The data sets that are used are different. So for warm start, we've picked only items and users that we have seen relevance for during training. And because we want to train one model, which is able to test on both data sets, so the evaluation, the discrepancy is due to the evaluation set and due to the fact that we use the same model.
So you did not like you only showed us the recall curve, but you didn't see the precision curve. Does the precision curve matter at all?
For our experience, the recall curve matched very closely with offline but held out test set. So that's why we chose recall. And you can read more about this in the paper. And we also computed the precision, and it looks very similar. So we didn't feel the need to show both. Yes.
Have you experimented with doing dropout on both users and items?
So the way we apply dropout is stochastically on both user and items, but we don't prescribe a logic to which we only apply user or item. So they are both dropped out with a probability of a preset probability. But it might be interesting to look at different logics of how we can apply these dropouts.
I'm actually going to use this. Hi everyone, I am Mo from Wattpad. I'll be talking about session-based recommender systems. For those who don't know what Wattpad is, it's a social platform where writers and readers connect through stories. So if you, when you go to Wattpad, this is the home feed looks like on the left. So you get to present, you are presented with lots of recommendations. Some of recommendations are based on your recent interests. Some are based on content based and so on. I'm going to actually talk about the one that I mentioned in the red square, which is the what to read next. It is based on your user's sequential reading behavior, previous reading behavior. So what it does, it basically takes into account your previous history in sequence and tries to predict what stories you're going to read next. Okay. So first of all, why did we take this? Why session-based? So at Wattpad, what we have seen is different people read different types of stories based on different contexts. Like people read during the morning time, they would something different than the nighttime. When people use in a subway or in the commute, they try to read different type of contents. So context is very important for us. And also, reading is a type of activity which happens usually in sequence. In Wattpad, there are also like story series, prequels, sequels, and also stories that are serialized. So sequence is really important for us. Okay, so using this traditional approach where the user and item metric interactions are presented in a big matrix, you have some known ratings, and the recommendation problem is to basically predict those missing values with some ranking function. So what essentially you're getting out of it is basically user and item vectors, which are kind of like user and item profiles, and they are also like very static. So what that means is if you pretty much get the same, almost same type of results if you just do a dot product or do some metric similarity with it. Of course, you could add more dimensions to it, like time and so on. But again, we really wanted to use the sequential, powerful sequential interaction that we have. So here is an example of sessions looks like. The top row represents one session, is a type of stories. Story, as users have read story 1, 2, 3, and the recommendation task is to predict what's the story user going to read next. Okay, so the bottom one is also another type of session. And as you can see, these both sessions are from the same user. The stories they're reading are completely different. So the top one is more of like a travel based. Maybe the user went on a vacation or something. The bottom one more of like a nighttime session where usually users try to read some like dark novel or something like this. So basically what we wanted to do, we want to basically, to solve this, we want to basically convert the recommendation problem as a multi-class classification problem. So, so here the input for the recommendation problem is like x1, x2, and so on, and we wanted to predict y. Okay? So in order to approach this, we use the recurrent neural network. So this is the architecture looks like. We have the input sequences, and we have the embedding layer, and we have some hidden layers in between, and we used LSTMs for this. And because we wanted to predict a score, so that's why we go with the softmax, and then we have the output. Some details from how the model was built. So we have used, okay, so first of all, we have tried different architectures and different values of these models and see which one gives us the best results. So pretty much we ended up choosing these parameters. So we have chosen 128-dimension embedding layer, 3 stacked LSTM layers, each contained 64 hidden units, 10 each activation for each of the LSTM layer, and we have added dropout to reduce the overfitting problem. Because it's a classification problem, we went for the sparse categorical cross entropy, and we used the RMS prop optimizers. Okay, so here is the training data set looks like. So we have 20 million users, 4 million stories. That consists over 100 million sequences. To reduce the sparsity of the problem, we have only kept the sequences which are at most 30, and also we have kept the sequences that are minimum at least 3 in size. So we have trained the model in a mini batch fashion with 1024 on each mini batch. We have implemented is with Keras with TensorFlow backend, and it was trained on an 8 GPU, which took us 2 days to train it. But the training is not crucial because ideally we don't want to train on a daily or a weekly basis. So ideally what the deep learning model comes into play, you basically train once and you try to infer more. So when you have some new inputs, you basically add those inputs to your vector or tensor, you basically infer to get the results. Okay, so we ran an online experiment with it. So the experiment data sample size was about 1 million user. We split into 50-50 traffic, and we used the normalized mean reading time to evaluate. So what we have found was for experienced users, we have seen 39% increase in reading time, and for new users, the improvement is much more. We have seen 82%. For new users, basically the way we calculate the new users are users who have signed up in last 2 weeks. The reason we think that it has a massive impact for new users is because when the new users signed in, they wanted to get the recommendations as soon as possible. So, so this model can predict your input sequences very, very quickly. That's why it has a very, very high impact on the new users. Okay. So some of the learnings that I wanted to share was the new, so the modern deep learning technology, it opens the door to a bunch of whole new possibilities. It helps you to use powerful representation which were not done before. For example, if you wanted to use any site information like image data, any metadata, it's very easy to do with deep learning, and it also has much more flexibility than previously. For example, if you wanted to write your own SGD, or if you wanted to do a custom loss function, it's very easy to do with the modern deep learning technologies. Although we have seen very good results with the sequential recommendations, it might not be the solution for every type of application. So you really wanted to play with to see if the sequential activities matter to your application or not. Okay, so and it's also not straightforward. So you have to do lots of pre-processing and post-processing to make it work properly. And my suggestion is that it's better to try with a smaller data set with a simple architecture, and that's also what we did. So we didn't want it to go with much, because it's our like a very first deep learning based RNN based implementation. We wanted to keep with the simple architecture, try with what we get out of it, and then try to optimize it after. But when it works, it's highly rewarding. So it gives you really, really amazing results. So our work has been inspired by some of this work, and I can take a few questions if you'd like.
How often actually does something
So we currently, so it's a the way we do it. It's an API that we try to predict like every 10 minutes based on your recent activity. So if you are in that session, and it's basically every 10 minutes, it's try to see if you have made some progress on your reading behavior, and only then you're gonna get new recommendations. Does that answer your question? Or?
It's a way more of like the existing baseline basically if I just hard code and I'm reading
So we don't have any specific number of items that you need to read. So what we do as soon as you make some progress, so you read some story, and then it basically sends an event to a recommender system and basically generates recommendations for you. So you do not have to read like certain amount of reading story at first or something like this.
Your most basic recommendation is the number of items you could recommend.
Yes. So in our first implementation, it was a big deal because we have, so the number of classes are pretty much the same number of stories. So we have tried to reduce that number using some stories that do not qualify, like really, really bad stories, those kind of stuff, but that was not good enough. So we actually wanted to tackle this problem in the second part of our implementation, which we wanted to use the Bloom embedding, which is kind of Bloom filter-based approach to reduce the sparsity of the overall number of classes. So you basically require less amount of resources to basically feed the entire embedding space. So there have been a recent paper regarding this. So at some point we wanted to actually try to see how it has an impact.
You should have one more else here.
Yes, so we actually tried more, and we didn't see in substantial gain after this. So we are basically adding some overheads. So we decided to stick with 3. Maybe in the next few iterations, we want to actually try different loss functions or something like this, rather than just increase the number of hidden layers to see how does it impact. Yeah, we didn't see substantial gain increasing the number of hidden layers. We see the training time would go up definitely, but didn't increase the accuracy that much. 1 to 3, yes, but when we try to increase from 3 to 5 or 3 to 7, not much gain. But that might be our problem specific. Yeah, so we compared with the non-sequential based recommendations versus the sequential based one. So for existing users, we have seen 39% lift in reading time, normalized mean reading time. And for new users, we have seen 82% lift. So that's another. So that's a different type of recommendation that we usually deal with. So we have a recommendation module that deals with the colder items. So that type of in that recommendation type of module, we basically see if a colder model probably we try to predict if it's probably going to be popular pretty soon, but is not quite popular yet. So and then we basically try to include it into recommendations. But also we in another type of recommendations we have some metadata-based approaches as well. So that also helps the cold start.
So the more general question.
Yes.
Some time ago, you guys had a blog post about live events, and it seems like you're embracing global approaches to a lot of stuff scientific concepts.
Yes.
Can you characterize where you work where they work well, and where you
in my opinion, deep learning problem works really well for if you have like a denser data. It works really well like a image data or textual data. It works really well. Recommendation is a little bit tricky because it's not dense. It's sparse. So you have to do lots of pre-processing to actually make it fit for the deep learning. But like I said before, if you do enough pre-processing and make it work, you get amazing results. Yeah, so I didn't include here. So some of the pre-processing steps are, so when you have some sequence, right? So we wanted to create subsequence of that initial sequence so that it can predict, it have more information on each of the so let's say if you have five items with, if you have one sequence with 5 items, right? And so the way you probably would basically train the first 4 items as an input and the 5th item out. So you're basically getting rid of all the information that you have seen in the first 4 items. So you want to pre-process so that you can basically create chunks of that 5 items, right? So for example, 1, 2, 2, 3, all the possible sequences of that, and you can also add some padding to it. So that's how you basically increase your possibility to the sequences.
Questions about the input representation. How much do you know about the systems of the content of the producer and the user to Facebook user as well as
so right. So we have story description, we have title, we have tags, we have even the story raw stories text. But in this recommendation, we haven't used any metadata. We only use the interaction-based information that we have. But we also have a lot of information, like we have covers, we have comments, usually put comments in the story, and we have seen some useful results based on the story comments as well. Thanks.
So last up, we have Javier from Rubikloud. Presentation. You don't want to put that around
Yeah, that one. Oh, the next slide comes. Yeah, okay. Yeah, cool. Okay. Hi, I'm Javier. I am part of the data science team at Rubikloud. We, at Rubikloud, I think I need to kind of contextualize the problem because otherwise it's going to be weird. We serve big retailers. We convince them to give us their data. And then after they give us their data, we offer them services on their data. So we modernize their infrastructure on our side. And then what we do after that is we offer services based on that modern infrastructure. So the type of services that we offer is basically we try to improve core operations inside the retailers. For instance, we want to predict, say, we want to help them allocate products in different stores according to the promotions they want to offer in 3 months. So we try to forecast how many products they are going to sell on this particular item under this or that particular promotion model that they have. And then they go for it, and then, well, we predict it, whatever. So the other part of the other type of problems we offer is we try to help them with marketing, individualized marketing. So that I am kind of part of the team that does that. And of course, part of the individualized marketing is the marketing teams every now and they actually kind of on a regular basis, they want, say, 50 million recommendations for 50 million users. And then what they do is they have different channels to reach these people, and then they send these recommendations. They do it over and over and over and over again. They want to have something like that available. They cannot do it with their infrastructure, so they rely on us. So that's more or less the context of what I'm going to talk about. So recommendations are a tough problem. How do I move this shit? Okay. Oh, I see. Okay. So it's a tough problem. It's not a prediction task. It has quality. It's not. That's very, very important. These recommendations for us are not a prediction task. We don't want to know what they are going to buy. We want to know what they would buy if we offer it to them. And that changes the whole perspective because this is almost impossible. You don't know. You don't know ground truth unless you do experiments. So it has a qualitative component. We want to offer something that generates a relationship with the customer. We want to fake something that is very natural when you go to a small store. When I go to Kensington Market to this Mexican store, they get my Colombian accent, and then immediately start telling me, hey, we have this guava thing that you guys love. And I'm like, sure. And then I start just buying because they know me. They know me for like 3 little things. So that's the type of stuff that we want to do. We want to get information from our users, either from transactions or from who they are, and then we want to establish a relationship between the merchant and our customers. We cannot just stop at any point. We need to continue exploring and experimenting. It's a kind of always, it's like an eternal randomized experiment. We need to set up something like that. So that's the context. Oh shit. Okay, so when we think about this problem internally, the way we think about this problem is as some sort of representation problem. We have a set of customers and a set of products, and then we have some sort of relation between customers and products that is weighted. That says something like the number of transactions that the customers have given a certain product or whatever. Sometimes P and C are actually kind of geometrical objects. You have your customers, and your customers are of different types, so you kind of find some sort of variety where they live. And the same happens with the items, especially if you have many. So what you want to find is some sort of space where both customers and products live, in which you can kind of define some sort of relationship of affinity. That tends to be some sort of distance, but not quite. So that's more or less the way we think about this. And then what it becomes is what you've seen before. This is like the standard slide that you are forced to present always. You start with something like that relationship over there. Then you represent that relationship as some sort of matrix in the classical case. Then you factorize, and then you get representations of customers and products in the same f-dimensional space for an f that you decide in advance. And then you minimize something like this. And then it becomes more complicated. Sometimes you don't want to, usually in our case, for instance, we know what they have bought and we know what they haven't bought, but we don't know which one is good and which one is bad. So we have information over the whole matrix. We have a lot of zeros and some places where we have numbers bigger than 0, and the zeros don't say, we are not trying to fill up this matrix. We are not trying to, how do I say it? We don't want to, we are not trying to do some imputation process here. What we want to do is to guess what is the affinity between products and customers, whatever that means, with very few information. So you do something like this, it becomes more complicated. And then, of course, there are some other ways. You can change factorization methods, and then instead of considering some sort of like this, in this particular case, this is like a Gaussian type of thing, then you can consider Poissons for the representation of the relationships, something like that. You can use topic modeling. You can use entity-to-vector type of algorithms. You can model the sequence of transactions like our friends from Wattpad. And what we've noticed is that in our case, at least, the first three things kind of make sense. The last one doesn't quite, because, you know, like big retailers, these people go every now and then. You have, in 5 years of data for 50 million people, you have 9 transactions per person, something like that. They are not very long. These are not very long sentences, so there is not much to learn from there. But the other 3 are kind of cool, and they work. So what we've noticed is that when we want to actually try to come up with a way of recommending things that are interesting for them, a mix of them is preferable. So you have 3 different representations or 4 different representations, and you're trying to mix them up together. So then you get there, and then you're happy because you already solved the problem that the customer has. And you go to the customer and you say, hey guys, look, I have 6 recommendations for your customers. And then the client says, actually, that's okay, but it's not really what we were looking for. And then you start asking them questions. And when you ask them questions, you realize that they actually want a lot of things that they weren't saying before, because they are big corporations related to other big corporations. There are some legal clauses, there are some contracts, deals, and a lot of shit. And all that shit together makes that problem even more complicated. For instance, they don't want this brand and this brand together in a set of 6 recommendations. Why? I have no idea. But they don't want them. You can have either one or the other. Or more reasonable stuff, they want at most M categories or brands in the set of recommendations. They want a certain amount of money, which is the minimum for the recommendations. They don't want to mix certain people that they call luxury with certain products that they call luxury with some other products that they call mass, because then they feel that people are going to get mixed signals about who they are. Because remember, recommendations are about telling the person, hey, we get you. We get you. That's all they want. They want to reinforce this idea that these merchants know the people who are on the other side. And so that's the reason of some of these restrictions. Some other restrictions come from seasonality. So certain products have their moment, act accordingly. How do you do that? It's hard. It's hard. How do you know, for instance, we had this idea. Let's say sunscreen. So sunscreen is for the summer, and it is for the summer. Then you start looking at things, and you realize that there is a spike in December. And it's because people go to the south in some places. And then it becomes complicated, it becomes geographical, it becomes temporary, things happen. Replenishment, pairs of customers and products are recurrent, take that somehow into account. Or just general messiness, they know what is what, but they don't know what is what. For instance, there is this index here, and they claim that this index identifies a product modulo versions. For instance, nail polish in different colors, the same type of thing. And then you realize that that index is broken somehow. There are some products that even though they are actually the same that this other product in another color, they have different identifiers because of messiness. These are old companies with legacy systems. Nobody knows what's going on, and you need to fix that thing on our side because we don't want to give them two nail polishes, one red and one blue if they are the same brand, the same type. So we want to fix that somehow. So our solution right now tries to address these types of problems. And so what we do is a two-stage solution. We have 3 or 4, I think 3 right now, 3 representations of products and customers. One of them is a simple matrix factorization. Another one is some sort of word-to-vec type of thing. And then there is another one that is like super naive, using basically bags of words. And then for each of those things, we generate for each customer a long list of recommendations, hundreds. And then what we do after that is we use linear optimization. It turns out that most of the requirements here can be described as linear optimization constraints, or they can be described as things that you can put in the objective function of the linear optimization problem for the particular customer. So we use linear optimization for ensembling affinities. We have the 3 representations. We basically what we do is we write an objective function that gives different weights to each of the representations for the product for the particular customer. The other thing that we do is we fulfill restrictions, all this craziness that they have there. We encode that as constraints. Those constraints, by the way, are changing kind of constantly. Like this time they want this time they want that. Sometimes they want some emphasis in a certain category, et cetera, et cetera. So we need to be very, this thing needs to be very configurable. So we wrote something that allows us to basically encode most things in a configuration file, and then the configuration file is fed into the system and the system figures it out. So fulfilling restrictions, and finally, injecting extra features pre-selection. If there are certain features that are user product, and if you have 50 million users and 100,000 products, calculating one number for each pair is expensive. So you want to do it fast. So what we do is we pre-select first. We reduce the amount of pairs that we actually want to calculate. And then we have some pre-trained models that we can use to calculate the values that we need. We feed all that into the linear optimization for each customer, and then we get some selection. So the way the flow looks right now is you have 3 recommendation systems of sorts. You have something that we do is, and it's practical, is you have 50 50 million customers, you have 100,000 products. You don't want to calculate the distance between these two things for every pair 3 times. So what you do is you encode the representation of the item set using an index, using an approximate nearest neighbor index in a tree, and then that's the thing that you look for. So you don't get exactly the closest to 100 items, but you get something that works. So after that, we get a preselection of the 200 items for each of these things. Then we inject the product and customer models that require lots of computations. Then we do a linear optimization for each customer, and at the end we get selections. For doing this, we use a mixture of Spark. Annoy is a piece of code that allows us to do this. Sklearn for certain models. Pulp is a package that allows you to describe easily linear optimization problems, and Stan for certain probabilistic models. And then we put this inside a flow orchestrated using Luigi, essentially. And it works. Right now, there is another talk where I tell you how hard it was to make this work in a reasonable amount of time. But the long story short is that the first time we tried to run something like this, it took like 36 hours and it was not finishing, and we were like, why? There is something broken here. And right now we are more or less around 6 hours for that data set that I've been talking about. And we do this every week. We actually do it twice because we are doing constant A/B testing. So this is to wrap around an A/B testing infrastructure so that we can throw different types of configuration of this thing into the customer. And we are always evaluating what's happened and then acting accordingly. So, but we would like to jump higher. So there is this thing that they do. That thing was an Olympic sport like in the 1920s, by the way. I'm always amazed at that. Anyways, custom graphs of relationship between products. Yeah, so what happens is that you go where your marketing department is, and they actually have some ideas of how things should be related. They are vague, but they want us to somehow come up with a way of implementing them. So they have a vague graph of relationship between, say, customers or items or a mixture of both, and then how the hell do we turn that into something that is taken into consideration by our system? So we've been looking for ideas for that, and we found that there is this technique called retrofitting that is used for language people to basically perturb the word-to-vec space using some sort of given graph of relationship between the objects. So that's something we are exploring. Something that we're also exploring is that most of what we do is based on transactional data right now regarding the recommender. We would like to consider, as somebody was asking in the previous talk, more information, because actually we have more information about these customers. So we've been looking at factorization machines. They look promising. We want to see what's going on there. Then there is the problem of there are some people who actually hate the recommendations. So we want to help our clients decide to whom should we set recommendations and to whom we shouldn't. And so we are building some sort of heterogeneous treatment effect model for that. And then we're going to try to fit it inside our already kind of complicated infrastructure. And then finally, my personal dream is, and this is something we've been discussing lately, is how do we turn this into some sort of reinforcement learning problem? Each customer has very few interactions with the entity, with the client, but we have hundreds or thousands of millions of interactions within a year. So we want to maybe use the collection of this information to try to set up some sort of basic, very, very basic, adaptable recommender system that kind of learns as time passes and as information becomes different, then the system the system adapts. So that's kind of my personal dream. We are reading some papers about it. So further reading, just in case you want to read about some of the stuff I mentioned. The first paper is the classic. It's 2008, but that's already a classic because everybody's doing deep learning now. So that thing is the one where they describe this collaborative filtering with the matrices, implicit feedback. It's a really nicely written paper. This is the second one is something that I am playing with lately. I am trying to implement this using Stan just to see what happens. It's using Dirichlet allocation for topic modeling, and then a little bit like a variant of that. The factorization machines paper by Rendell, and the higher order factorization machines by Blundell et al. The first one is theoretical, the second one is more practical. They try to show you how to do that efficiently. This paper about retrofitting word vectors to semantic lexicons have been interesting, and I think it's promising. I think we're going to implement it very soon. And then finally, for our dream, this is more or less the reason our dream is this paper by Silver, where they describe very broadly what would be the way as a reinforcement learning system would work in the context that we are essentially trying to address. So those are the papers I would like to recommend. And this is it. That guy with the stick is a guy recommending dried animals.